we're going to be looking into series and just sort of going back to some of the items you might have seen in Calculus 2 with Taylor series and MACLAURIN series, especially MACLAURIN series. And we have working with series, and we'll be looking at summations. And there are various types of series we'll be looking into, like MACLAURIN series, power series, and also just looking at solving differential equations through the use of using series. And this will have a bit of a micromanaging feel to it, but it's a bit of preparation for some of the final stuff we'll be looking into, especially the method of Frobenius and the Bessel function. And tell you what, just with MACLAURIN series, so we go ahead and get right to it. So we have for a function f of x, we have is equal to the summation as n goes from 0 to infinity. And for the f to the n of 0, okay, the n is going to be in reference to the order of the derivative of the function f of x whenever x is equal to 0. And we have all over n factorial times x to the n. And just to kind of give you an expanded notation, okay, so we have for f of x, so if I take, let's say, the first few terms of the series, starting from n is equal to 0, so you have f of 0, no order in the derivative, and we have all over 0 factorial times x to the 0, and again, x to the 0, okay, is going to be equal to 1, and then we have plus f prime of 0, and then we have all over 1 factorial times x to the first, and you have the second order derivative of f is 0 over 2 factorial times x squared. Then you have the third order derivative of f of x when x is set equal to 0 all over 3 factorial x cubed, and so on. And again, just for what we have in the pattern for factorials of whole numbers, 0 factorial is equal to 1. And 1 factorial is equal to 1, and that could also be written as 1 times 0 factorial. And you have 2 factorial is going to be 2, or 2 times 1. And you can also write this as 2 times 1 factorial. And 3 factorial, which would be 3 times 2 times 1. In other words, the product of the first 3 natural numbers, and that can be written as 3 times 2 factorial. And for 4 times 3 times 2 times 1, the product of the first 4 natural numbers will be 4 factorial, which is 24, and that can be written as 4 times 3 factorial. And the reason I'm adding this stuff in red is that I'm going to kind of use this as a prelude to what we'll be looking into with the gamma function. And we'll be looking at this in the capacities of working with series, and also for what we will be looking ahead into with Laplace transforms. And let's say that, okay, just as a sample, of looking at MACLAURIN series. Okay, so we have, again, just 0 factorial is 1, 1 factorial 1, 2 factorial 2, and so on. So we have f of x is equal to f of 0 plus f prime of 0 times x, and you have the second order derivative. We have f double prime of 0 x squared over 2, and you have plus a third order derivative times x cubed all over 6, and so on. And just some of the samples of functions we'll be looking at in terms of writing in terms of the MACLAURIN series representation. And let's say if we are looking at f of x is equal to e to the x. Okay, so if we take like f of x equal to e to the x, and let's say out to the third order derivative, well, that's going to be locked in as e to the x. And guess what? Assigning x at 0, like we have f of 0 all the way out to the third order derivative f of 0, and you have it locked in at e to the 0, and we have 1 throughout. And in accordance to what we have with the MACLAURIN series, so assigning f of 0 all the way out to the third order derivative of f of 0, okay, that's going to come out to 1. So we have f of x equal to e to the x equal to 1. Then you have plus 1 times x. Then we have plus 1/2 of x squared. And we have plus 1/6 of x cubed, and so forth. And so that would be what we have in the terms of the MACLAURIN series for f of x. And for what we have in the case of another function. Okay, so we have with f of x equal to e to the x, equal to 1 plus x plus 1 half of x squared plus 1/6 of x cubed. And this will be used in looking at getting the MACLAURIN series of the function set equal to e raised to other powers. But for what we have, let's say that if we have in the trig function with the sine of x, and if I'm looking at the MACLAURIN series representation of the sine of x, okay, and you have with f of x equal to the sine of x, if I take the derivative of sine of x, this will go to the cosine of x, and the derivative leads to the negative of the sine of x followed by negative cosine of x. And once I get to the fourth order derivative, I'm back to the sine of x. And so we'll have a cyclical pattern going from sine to cosine to negative cosine of x. And the reason I have written out all these excessive terms is that I am looking at the first four non-negligible terms in the MACLAURIN series. And notice we have whenever the function or any derivative comes out to positive or negative sine of x, we have f of 0 or whatever order of the derivative of f of 0 comes out to 0. And the only non-negligible terms we have arise whenever we have either cosine or negative cosine of x, and at 0 cosine leads to 1, negative cosine leads to negative 1. If we were to substitute in accordance, okay, so f of x equal to the sine of x, again, f of 0 is negligible, and in fact only the odd powered order of the derivative of f of 0 set will be non-negligible. Okay, so you're looking at first order, third order, fifth order, seventh order, and we have for f prime naught of x, okay, this will be 1 times x, and we have third order derivative, again we have negative 1 times x cubed over 6, so we have leading to negative 1/6 of x cubed. And we have, for the fifth order derivative, we have a positive 1. Seventh order, we have a negative 1. And so we have the next two terms. We have 1 over 5 factorial, which is going to be 120 times x to the fifth. And we have minus 1 over 7 factorial. And 7 factorial is going to be 5,040. And so this leads to minus 1 over 5,040 times x to the seventh. And for what we have with the cosine of x, okay, and notice here with the sine of x, you have this set of terms, and without having to take the repetitive use of the derivatives of cosine of x, if I already have the MACLAURIN series for the sine of x, well, guess what? Cosine of x is going to be the derivative of sine of x, and if I take the derivative of the MACLAURIN series for the sine of x, okay, we're going to have the derivative of what we have in the set. And so for the first four terms in the MACLAURIN series that defines the cosine of x, we have 1 minus 1 half of x squared plus 1/24 of x to the fourth minus 1 over 720 times x to the sixth. And now, again, I had mentioned that what we had attained when we arrived at e to the x, that I would be reusing the MACLAURIN series. And let's say that if we have f of x is equal to e raised to the 2x, well, guess what? If I have the MACLAURIN series in store from e to the x, what I can do is that I can take this formula or this representation, and in finding out what the MACLAURIN series for e to the 2x will be, well, I can take the algorithm for e to the x, and where I see x in the expansion, I'm going to replace with 2x. So I have like 1 plus 2x, and you have 1 half of the square of 2x. The square of 2x is 4x squared. And we have plus 1/6 of the cube of 2x, and the cube of 2x is going to be 8x cubed. And so for e to the 2x, you're going to have 1 plus 2x, and you have plus half of 4x squared, which would be 2x squared. And you have 1/6 of 8, which is 4/3 times x cubed, and so on. So this arrangement will consist of the first four non-negligible terms for what we have in the MACLAURIN series for e raised to the 2x. And let's say that if we have complex numbers, say if we have with e to the ix, and again, let's say if we have whole number powers of n equal to 0, 1, 2, 3, 4, and where we have I is equal to the square root of -1, we have for I to the 4th n. This would be like where you have equal to I to the 0, I to the 4th, I to the 8th, and any non-zero value raised to the 0 power is equal to 1. And for I to the 4n plus 1, and this would consist of I to the 1st, I to the 5th, I to the 9th, and that will lead to I. And for I to the 4n plus 2, we have that in the set to consist of I squared, I to the 6th, I to the 10th, and for I squared, this would be like I times I, or the square root of -1 times itself, and that will become -1. And for I to the 4n plus 3, we had to consist of I cubed, I to the 7th, I to the 11th, and you can say that is equal to, in this case, I squared times I, or -1 times I, and that will lead up to -I. And for what we have in the case of e to the ix, if I take the e to the x MACLAURIN series and replace x with ix, so I have like 1 plus ix plus half of the square of ix plus 1/6 of the cube of ix, and notice we have in expanding. Okay, so you have 1 plus ix and 1/2 of I squared x squared. Again, I squared is -1. And for 1/6 of I cubed x cubed, I to the 3rd, again, is going to be -I. And so we have in the expansion, we have f of x is equal to e to the ix. And we have among the first terms, we have 1 plus ix minus 1/2 of x squared minus 1/6 of ix cubed, and so on. And going back to what we had when we were dealing with the Euler equation upon first looking at second order homogeneous equations that consist of complex roots. Again, we have e to the ix is equal to the cosine of x plus I sine of x. Again, you have this set for e to the ix. And from earlier, we had these terms from the MACLAURIN series of the cosine of x. And for the sine of x, I had x minus 1/6 of x cubed, and so on. And multiplying this set by I, notice we have consistency here where we have e to the ix with this set of terms. And combining what we have with the cosine and I sine of x MACLAURIN series terms, okay, notice you have 1 plus ix minus 1/2 of x squared minus 1/6 of ix cubed, and so on. And so we have verification by the MACLAURIN series that e to the ix is equal to the cosine of x plus I times the sine of x. And for what we have in the case of e to the x squared, so if I take the e to the x series and replace x with x squared, okay, so I have 1 plus x squared plus half of the square of x squared plus 1/6 of the cube of x squared, and among the first terms will be 1 plus x squared plus half of x to the 4th, followed by 1/6 of x to the 6th. And if I look at integrating, now if you try to integrate e to the x squared dx, you'll come out to an imaginary error root function. But in terms of making this feasible, in terms of variable expressions, you could take the first few terms of the MACLAURIN series of e to the x squared and integrate with respect to x. So I'll be looking at integrating 1 plus x squared plus half of x to the 4th, 1/6 of x to the 6th, and so on. And we have for the integral, we have x plus 1/3 of x cubed plus 1/10 of x to the 5th plus 1/42 times x to the 7th, and so on. And the more terms you have in the expansion, the more precision you will have in terms of integrating with respect to x, the function where we have f of x equal to e to the x squared. Now, also a bit of heuristic in terms of making what might otherwise be a perpetual taking the inverse and chain rules of ratios. Say if you're looking at the MACLAURIN series for 1 all over 1 plus x squared. First of all, what you can do is a little bit of a shortcut. Instead of having to take the derivative of the reciprocal of 1 plus x squared, you can start out with working with the reciprocal of 1 plus x. And just for the derivatives, okay, you have 1 over 1 plus x leads to the negative of the reciprocal of the square of 1 plus x. Then the next derivative, you have 2 over the cube of 1 plus x, followed by negative 6 over the fourth order of the quantity of 1 plus x. And just for f of 0, that leads to 1. And first order derivative, we have of f of 0, that is equal to negative 1. Next order, we have 2. And third order, we have at negative 6. And so we had the tools to have 4 non-negligible terms. Now for 1 over 1 plus x, you're going to have 1 minus x plus x squared minus x cubed. Notice you have alternating positive and negative values as we have the monomial x to go up 1 degree at a time. And if I were to replace what I have here in x with x squared to get to what we are originally looking for, so for 1 over 1 plus x squared, we have 1 minus x squared plus the square of x squared, which will be x to the 4th, minus the cube of x squared, which will be minus x to the 6th, and then we have plus x to the 8th, minus x to the 10th, and so on. And for the MACLAURIN series of the arctangent or the inverse tangent of x, well, by definition, the arctangent of x is going to be the antiderivative of the reciprocal of 1 plus x squared. And so just taking the integral of what I have just attained for the MACLAURIN series of 1 over 1 plus x squared, we're going to have among the first terms for this function, namely the arctangent of x, we have x minus 1/3 of x cubed plus 1/5 of x to the 5th minus 1/7 of x to the 7th, and so on. And that would be what we have in the series for the arctangent of x.